Hello, thanks for tuning in. The results presented here are based on an Air Force technical report listed here. It's available for free downloading at www.dtech.mil.
Hi, my name is David Wayburn and I will be presenting a short PowerPoint slide movie on boundary layers formed by fluid flowing along a wall. The theoretical approach to describe fluid flow is in general based on the conservation of mass, momentum, and energy equations. This set of partial differential equations are in general very difficult to solve. There are few analytical solutions. Even computer-based numerical solutions are difficult. The computational effort for even a simple turbulent flow can take hours on a supercomputer. Hence, one looks for other solution approaches. One of these involves the concept of similarity. That is, in certain flow situations, the flow at one measurement station will look similar to the flow at a second measurement station, differing only in the scaling of the flow features. By employing dimensional analysis and scaling parameters, we can convert the flow governing partial differential equations into ordinary differential equations. This can result in 3 or 4 orders of magnitude reduction in the computational effort. Boundary layer flow is one of those flow situations where similar solutions are known to exist. The key to finding similarity solutions is to identify the scaling parameters. For the turbulent boundary layer, what is done today is to simply guess at what scaling parameters might work and then apply the guesses to experimental profiles to see if they work. In this short video, we will look at a new way to determine the correct boundary layer scaling parameters using a theoretical approach. Okay, so let's go.
Here is a schematic drawing of a boundary layer flow along a thin flat plate. The fluid is flowing from left to right along the plate. The plate and the flow extend in the plus minus z direction. The velocity profile is defined as the velocity at x for all y. At the surface of the plate, the velocity is 0 due to viscosity. It then slowly increases to the asymptotic flow value u sub e. The point the velocity recovers to u sub e is the boundary layer thickness, shown here as the red line. That thickness will increase along the plate since more and more slow-moving fluid piles up. Under certain conditions, the scaled velocity profile at x1 will look similar to the scaled velocity profile at x2. The two velocity profiles are said to be similar if they differ only by scaling parameters in y and u at xy. Let's take the length scaling parameter as delta sub s, and the velocity scale parameter is u sub s. Mathematically, the definition of similarity is written by this equation here. The key to finding similarity solutions is identifying these two scaling parameters. The traditional approach to similarity utilizes a stream function approximation. See Schlichting's book for further details. Now, let's turn to the new similarity approach and how we determine the identity of delta sub s and u sub s. The new approach is based on a simple concept. For similarity, the area under the properly scaled velocity profile curves must be equal. To see what I mean, consider some of these velocity profiles shown here from Scari and Krogstad. These profiles were measured at 7 stations along their plate. What you do is sit at one spot and measure the velocity at 40 or 50 spots above the plate. These are the type of profiles you get when you do that. Now, if we knew the right similarity scales and plot all of the scaled profiles on one graph, then the scaled profile should collapse to a single curve. In fact, this is exactly what we show here. All 7 profiles plot on top of one another. Just as a preview of what's to come, This collapse was accomplished with U sub e and delta sub 1, where delta sub 1 is the displacement thickness. Our intent here is to prove that U sub e and delta sub 1 must be similarity scaling parameters. To do that, I want you to look at the scaled profile plot. Notice that the area under the curves will all be equal. This is important because we can describe this area mathematically. The area under the scaled profile is given by this equation. A necessary but not sufficient condition for similarity is that the calculated area values for each velocity profile in the set must be equal. Now, it turns out that this particular area integral is not very useful in its present form. We need to do a few more steps to get to something useful. Instead of starting with the similarity of the velocity profile, consider the first derivative profile. If similarity is present in a set of velocity profiles, then it is self-evident that the scaled first derivative profiles must also be similar and the areas equal. If the scaled velocity profiles plot on top of one another, if they are essentially identical, then obviously the derivatives will also look similar. The area under the first derivative curve is given by this equation. It turns out we can calculate this integral directly. Using a simple variable change, it is pretty straightforward to show that this integral will always calculate out as U sub e divided by U sub s. For similarity, the areas under each velocity profile must be equal, which means this ratio must be constant if similarity is present. So, using our new approach, we have just determined that U sub e must be the velocity similarity scaling parameter. It turns out this same result is obtained in the traditional similarity approach. Refer to the papers listed here. Okay, we now know the velocity scaling parameter. We still need to find the length scaling parameter. Alright, let's get back to our integral area story about the velocity profiles. Using the first derivative result, we can state that if similarity is present in a set of velocity profiles, then it must also be present in the calculated defect profiles. The defect profile is defined as U sub e minus u at xy. We just showed that U sub e divided by U sub s must be a constant. Subtracting a constant from all of the areas will keep the areas equal. This is kind of a remarkable result. The turbulent boundary layer community has fixated on the defect profile for the last 60 years to the point that they will only discuss defect profile similarity. Yet we have two different theoretical approaches that says that similarity must be present simultaneously. Alright, back to our story. Looking at the two profile plots, it is evident that the areas under the curves in each case must be equal. Mathematically, the area under the scaled defect profile is given by this equation. Using the same technique we used on the first derivative integral, using a simple change of variables, it is easy to show that the area integral reduces to this simple ratio. The key, of course, is the displacement thickness definition integral. Now, similarity requires the areas must be equal, which means that this simple ratio must be constant for similarity. The importance of this new similarity constraint is that the length and velocity similarity scaling parameters are not independent. You cannot choose any old parameters for the length and velocity scales. Their product must satisfy this ratio. Okay, this is new and kind of interesting. However, the most important result from this integral-based ratio comes about when we combine that with our earlier result. We can now state that the length scaling parameter must be the displacement thickness. This is a brand new result. In the more than 100 years of work on boundary layers, this is the first time that the length scale has been determined to be the well-known displacement thickness. If similarity is present in a set of velocity profiles, the length scaling parameter must be the displacement thickness, and the velocity scaling parameter must be the velocity at the boundary layer edge. This is regardless of what type of fluid is flowing along the wall. It doesn't matter if it's non-Newtonian, turbulent, transitional, laminar. It does not matter. Delta 1 and U sub e will be the similarity scaling parameters that work. Do non-Newtonian boundary layer flows display similar behavior? I do not know the answer to that question, but I do know that if any fluid flow displays similarity, delta 1 and U sub e will be the similarity scaling parameters that work. The results are only dependent on our definition of similarity and the displacement thickness, our velocity profile model, and the velocity profile boundary conditions. It is easily verified that these new scaling parameters work for certain theoretical laminar flow results. But what about turbulent boundary layers? Theoretical solutions are not possible because of the closure problem. Therefore, the fluid flow community has tried to guess which parameters might work. To determine if the guess parameters work, they are tested on experimental data sets. Well, there's no need to guess anymore. To confirm that the new parameters work on turbulent boundary layers, we looked for experimental data sets for which U sub e and delta sub 1 might work. We already saw that this combination worked well for the Scari and Krogstad data sets. Here are some more results that I found. These are 6 direct numerical simulation turbulent profiles from Professor Solero's group in Spain. Over here are 7 turbulent boundary layer profiles from Professor Smith's group at Princeton University. Here are a couple more examples. 6 channel flow turbulent boundary layers results from a German group, and 7 more profiles from KTH University. A couple of important observations. We already discussed that this result applies to any flow situation that displays similar behavior. Also note that the new constraints are mathematically rigorous. Although not derived as such, it is possible to derive the constraints as mathematical proofs. Also note that there are no approximations or assumptions, nothing equivalent to the traditional flow governing equation approach, which assumes the velocities can be approximated by a product of x and y functionals, an assumption that can never be proven one way or the other. The present results run counter to the accepted literature results for the turbulent boundary layer. Some groups claim that most turbulent boundary layer datasets display similar behavior when scaled with the Zagarola and Smith's scaling parameter. However, these claims were made without verifying that all the similarity constraints were satisfied. Check out my recent YouTube video, a cautionary note on the Zagarola and Smith's scaling. One final thought. The equal area similarity approach can be used to discover other similarity requirements. For example, in these papers I show that the ratio of the velocity scaling parameter to the length scaling parameter must be proportional to the wall shear stress. Okay, that's it. Thanks for tuning in. Please send your comments or suggestions to the email listed here. Thanks again. Goodbye.